Okay, now in the remaining time today and probably tomorrow, we're going to discuss this generally titled lecture, Parallelism and Heterogeneity. But we're going to build on heterogeneity actually, but we're going to discuss a lot of interesting topics in parallelism also. And this is going to start transitioning us to the remaining, let's say, 1/3 of the course or so, which will be about a lot about parallelism and more about computation as well. We will talk about a lot of interesting topics and paradigms like multiprocessing, cache coherence, etc. Later on, and hopefully this will be interesting. But before I start, since I received a lot of queries about this from some of you, I will briefly mention some of the research opportunities that are in my group. And if you want to do research on any of the covered topics or any topic in computer architecture, hardware, software interaction, related areas, some of you have been contacting me. That's great, actually. We have many projects and a great environment to perform top-notch research. And hopefully that's coming through some of the works that I have presented. We have bachelor's, master's, and semester projects. So talk with me in some way. In person is harder these days, clearly, and apply online. So we have an online application system that you can easily find from my group's webpage. And clearly, there are many research topics we talk about. Everything that we discussed actually so far is a research topic, and everything we're going to discuss going forward is going to be a research topic, because this is, in the end, as I mentioned earlier in this course, my goal is to provide you both the fundamentals and the cutting edge. So at this point, I think you're seeing pretty much the cutting edge of the computer architecture, which you may not actually get in an old-fashioned, let's say, architecture course that may exist somewhere else. Okay, so many topics, memory, as we discussed, there are many issues in memory, and last lecture is an example of this: processing in memory, hardware security, new computing paradigms, machine learning for system design, and system design for various different, very interesting applications. And there's more, of course. I'm interested in general computer architecture, so anything that piques your interest, I may be interested in it. In the past, I've done a lot of different types of work also. And if you remember, our current research mission is building fundamentally better architectures. And these are 5 major focus areas: architecture, hardware, software, interface and co-design, systems, bioinformatics, and security. And these are 4 key directions that we covered in some way: secure, reliable, safe architectures, energy efficient, memory-centric architectures, low latency and predictable architectures, and architectures for various key workloads. And this is not by no means comprehensive, but this is just to jog your memory. And the research approach is really this way. We take the expanded view, as you have also seen, and especially, hopefully you're convinced of the need for this with an emerging to memory technology, for example, in the last lecture. And these are some of the major research topics that, again, I'm not going to go into the details. This I present in the first lecture, actually, but some of these may make more sense right now, since we covered processing in memory and DRAM, non-volatile memory, unified memory, and storage. These are all examples of data-centric architectures, actually, for low latency and low energy and high performance. And we also covered a lot of the low latency, energy, low-cost memories, quality of service, really unpredictable systems. And we talked about security and reliability issues, some of them in detail, some of them in less detail. And some example works we've discussed about architectures for machine learning, artificial intelligence, genomics, graph processing, and medicine also. There's a lot of potential for this. And this is almost limitless, right? How do you do the algorithm architecture, logic co-design? How do you exploit heterogeneity? How do you actually exploit 3D stacked systems is very interesting also going forward, I think. And we've also discussed the data-driven and somewhat data-aware architectures. So if you're interested, let me know. This is the group I've shown you earlier also. And if you want to know more about it, you can actually go and click this and go to the group webpage. You can also read our newsletter, which is over here. Okay, that said, let's jump into parallelism and heterogeneity, which is a fascinating area of research as well as practice for decades again. But some of the issues we cover are relatively soon. So this is what we're going to cover today and tomorrow. We're going to talk about some issues in parallelism, and then we're going to lead our way into heterogeneous multi-core systems. So, and then we're going to talk about bottleneck acceleration, identifying key bottlenecks, and how to potentially accelerate them. These are some readings we're going to cover. There are quite a few more that I'm going to reference that are not on the slide, but hopefully you'll find some of these very interesting. So let me first discuss heterogeneity in a broader sense, because this is, again, a principle. And we've looked at this principle a lot, actually, in this course. Asymmetry is a big principle in designing systems. And heterogeneity or asymmetry, these are two words that are used interchangeably. It leads to specialization in the end. This is one way of enabling specialization. They have the same meaning, and contrast this with homogeneity and symmetry, which sometimes may be thought of as good things, but sometimes they lead to scalability problems if you don't introduce heterogeneity and asymmetry into the system. And it's a very general system design concept and a life concept as well, clearly, right? And the overall idea is, instead of having multiple instances of a resource to be the same, in other words, homogeneous or symmetric, design some instances to be different or heterogeneous or asymmetric, basically. It's very simple, as you can see. And different instances now can be optimized to be more efficient in executing different types of workloads or satisfying different requirements and goals. So now you have actually enabled flexibility to specialize your system to different types of workloads or different requirements and goals at any granularity that you decide to manage this heterogeneity, basically. So it's very, very powerful in the end. So this is why I say heterogeneity enables specialization and customization of the underlying system to the executing workload or the goals. Okay, why do we want this symmetry in design, basically? So I think the answer is twofold, basically: workloads and metrics in the end. And maybe operating conditions, you can also add this, but it's fine. Essentially, the first one is different workloads executing a different system can have different behavior, and a single application can have different behavior and different phases of execution also, clearly. Different applications essentially clearly have different behavior. Different execution phases of an application can have different behavior. The same application executing at different times can have different behavior due to input set changes and dynamic events, clearly. Many examples of this different behavior: locality characteristics, predictability of branches, instruction level parallelism, data dependencies, serial fraction in a parallel program. We will see that actually later today. Bottlenecks in the parallel portion of a program. We will also see that. Interference, memory interference characteristics. At some point, the application may be interfering a lot because it's injecting a lot of requests to memory. At some point, it may not be injecting any requests because it has great locality, for example, right? Or what, for some other reason, because it's not accessing memory as much. Okay, so basically, we would like to adapt to these things. And the second, the systems are designed to satisfy different metrics at the same time. You almost never is the case that you design a system just for one metric. If people tell you, for example, there's even high performance computing, right? That's one example that I like to pick on. It's called high performance computing because people think performance is the only metric. No, unfortunately not. If you look at high performance computing, energy, power goes into a huge amount of design considerations that happens today. On top of that, cost. So these folks may tell you, I don't care about cost, but that's not exactly true, because cost in the end is always a design constraint, as we discussed, right? So basically, even some of the extreme systems are not immune to many different design metrics, as we discussed in the first lecture also, right? So there's almost never a single goal in design, depending on the design point, of course. I mean, if you constrain your design point enough, and if you design a specialized device just for one thing, maybe you can have a single goal. But again, even then, you need to design for performance and energy usually. So clearly, there are many metrics over here that I'm not going to go into the details of. And some of them are verifying a memory capacity, for example. It's maybe important independently of your performance, right? Because it may actually affect your worst case situations in terms of energy or performance or some other metric. Okay. So problem is that, so someone can say, okay, symmetric metrics are easier, symmetric designs are easier, clearly. So why is asymmetry interesting? And absolutely, symmetric designs are easier, but symmetric designs are also one size fits all. Essentially, a symmetric design tries to fit a single size design to all workloads and all metrics. And it's not possible, basically. It's very difficult to come up with a single design that satisfies all workloads, even for a single metric. And it's also very difficult to come up with a single design that satisfies all design metrics at the same time, especially if you're stringent on the design metrics, right? And this holds true for different system components or resources like cores, caches, memory, controllers, interconnects, disks, servers. Whatever you can imagine can be made heterogeneous. And if you're not heterogeneous, or if you're not asymmetric, then you may be losing the opportunity to specialize, which means that you may be losing the opportunity to satisfy many workloads at the same time and many design metrics at the same time. And this also applies to algorithms and policies that we implement in cache controllers, memory controllers, etc. For example, again, whenever you're not heterogeneous, you're not adapting well enough potentially to different metrics and different workloads. So this is my pictorial view of it. This is C is any resource. It could be a core. In the context of this lecture, we're going to talk a lot about cores actually. And symmetric means that the resources are designed to be exactly the same. And if you look at this as one size fits all, clearly, that's the mentality, mindset. Energy and performance is suboptimal for different workload behaviors. So one workload may actually require a fraction of this core, whereas another workload may require 16 of these cores, meaning a core that's of the size of a 16 of these cores, right? Or maybe 4 of these cores, I don't know, pick your choice. Basically, sometimes you need a very small fraction, sometimes you need a much bigger fraction, meaning this granularity, having a single granularity for your resource doesn't enable you to make any trade-offs in your design. Whereas having multiple granularities that look like this is an example asymmetric system. Again, this could be any resource, but it could be cores, maybe a big core, 2 medium cores, and a bunch of small cores, right? And maybe they have different characteristics, C4 and C5 in some way. So this is clearly asymmetric, right? And now you have the opportunity to customize and adapt. Why? Because processing requirements vary across workloads and applications and phases, as we've discussed in an earlier slide. And now you have the opportunity to design a scheduler or some mechanism that picks and executes the code that you are dealing with on the best fit resources to minimize the energy as much as possible while providing adequate performance as much as possible, for example, right? So asymmetry essentially enables you the opportunity to customize the system to your workload and to your wet metrics, whereas essentially you have no choice over here. For example, here you could have, if a core, if a system or if a workload required a big core, here you can have it. Here you have no choice. Now you can potentially try to dynamically reconfigure these cores so that multiple cores coordinate and act as one core, but now you're becoming asymmetric, right? You're not symmetric anymore, okay? Asymmetric doesn't mean that you're hard statically partitioned. Asymmetric means that you just have the capability to carve out your resources such that you have asymmetry in them. It doesn't say anything about dynamic, static. It could be actually dynamic asymmetry. Underlying substrate may be completely symmetric, but you actually have some ways of combining these small resources such that they can act like a large resource. It could be cores, it could be caches, clearly it could be memory controllers, I don't know, pick your choice. That is of course not so easy, not as easy as static designs like what this seems to be depicting, but it's also a possible choice basically. So symmetry and asymmetry are concepts, and asymmetry can be dynamic or statically formed. Okay, so keep that in mind because, for example, voltage and frequency scaling is actually an example of asymmetry that you can enable in otherwise symmetric cores, right? Some cores may be running at high voltage, high frequency. Some cores may be running at low voltage and low frequency. And maybe compute intensive parts that require low latency should be running at cores that are running at high voltage and high frequency, right? Because now you can actually, or critical parts of your computation should run over there potentially, right? It's good to keep that in mind. So you can achieve symmetry, you can achieve asymmetry in different ways. You can deal with, you can basically have more resources clearly, and that makes sense. You can have different types of resources like in order cores versus out of order cores. That makes sense. You can have different, the sky is the limit, actually. You can imagine different types of components that you may have or you don't have in the symmetric system. You can also change the voltage and frequency. You can do many different things basically to achieve asymmetry. And we hopefully tomorrow we're going to cover some different types of asymmetry as well. Okay, and we've already seen examples of asymmetry or heterogeneity before many times. So for example, if you take on digital design and computer architecture, you hopefully remember that the Cray 1 design, which is supposed to be the highest performance vector processor, it actually had a scalar pipeline as well, because they said it's way too inefficient to execute scalar instructions in the vector pipeline. I'm going to show you a picture of this. So they actually built the fastest scalar pipeline of their time, because they were scared of Dahls Law. Because if they could parallelize the program, they would be bottlenecked by part of the program that remained not parallel, right? And we're going to talk about Dahls Law again in a few slides. So modern processors have scalar instructions and SIMD extensions. Again, we covered this in digital design and computer architecture, and this is important. Again, this is another example of heterogeneity. In fact, SIMD extensions are growing in existing systems. They're becoming much more powerful, not as powerful as vector processors, but still not bad compared to general purpose processor. We talked about decoupled access execute. You have different types of processors doing different things. One of them is specialized for access. One of them is specialized for execute. We talked about in this course, thread cluster memory scheduling, different memory scheduling policies for different thread clusters. And clearly this is an example of heterogeneous scheduling policy, asymmetry. We talked about heterogeneous refresh rates in DRAM, how to enable that, radar. We talked about heterogeneous latency DRAM, hybrid memory systems. We just talked about it in a couple of lectures ago. And there are many different examples of this clearly that I think, covered all of them actually in some way. And we did not talk about heterogeneous cache replacement policy, but I believe I alluded to it in some lectures. So you can have multiple replacement policies within a component. So these are examples from the compute part, and these are examples from the memory part. And clearly you can increase the set of examples. It's not meant to be a comprehensive list. So you're already used to the concept of asymmetry, clearly. And let me jog your memory from digital design and computer architecture. This is Cray 1, and you can see that it has a beefy vector unit, but it has also one of the fastest scalar, actually the fastest scalar units of its time. And this is a heterogeneous design, and there's more heterogeneity clearly, as you can see. And we talked about hybrid memory systems. Hopefully you remember that easily. We talked about throughput versus fairness to optimize for different metrics, as you can see. And we talked about having single policy for all threads is insufficient when we talked about thread cluster memory scheduling. And we decided to have multiple different policies. I'm not going to go into the details, but there's clearly complexity associated with having multiple different policies, right? But it led to a better system in the end. Heterogeneous retention times, we talked about exploiting them. We talked about making the subarray heterogeneous so that you can get the best of latency and area as much as possible, right? If you remember these pictures, I'm going through these very quickly. My goal is to jog your memory, that's it. And these are all examples of heterogeneity, actually. This is tiered latency DRAM, you guys, heterogeneity. One thing we did not talk about, but we will talk about later on, is interconnects. So if you look at interconnects, so this is a system, Tylera system. It's one of the earliest very small multi-core systems for embedded systems. So it had 64 cores. Here you have example of 3x3. And 64 cores were connected to each other as a two-dimensional array of two-dimensional mesh network. So it was basically an 8x8 two-dimensional mesh. And each element had a router in it. Each processing element or each core had a router in it, and they could communicate with its neighbors. So the network had dynamic packet switching so that you could access from this core, and the cache slices were distributed across 64 slices, and there were 64, one slice per core. And you could actually, if this core, for example, needed to access this particular cache over here, it sent a message to route that. But there's no single network over here. There, due to different metrics to optimize and different types of workloads that go on the network, these folks decided to design 5 different packet switch networks. Actually, not all of them are packet switch. One of them is circuit switched, as you can see. 5 networks, on-chip networks. 4 of them were packet switched, and they used what we will discuss later on, different types of routing, XY routing, and some sort of full control. We're going to talk about that when we talk about interconnects later on. And some of them, one network was specialized to handle cache request packets, just requests. These are fast things, and these need to be delivered to the cache block very quickly. So they decided that you need a dedicated network for this purpose. Another was specialized for responses only. And again, this was important to deliver from some other network for multiple reasons. One is this way you can actually reduce potential deadlock issues on your network. And the other issue is response packets tend to be much longer. Cache request packets may be one small packet, whereas response messages may be 8 messages or 8 packets or 16 packets that need to go consecutively. So there's a lot more load on this network. So there are reasons why you actually design these networks differently. One network handled IO packets. One network was specialized for core-to-core messaging, for synchronization, for example, as we will discuss in this next lecture. And one network was circuit switched, because packet switching, meaning in each router deciding what to do separately, they thought this was too much overhead, especially if one core is communicating data to another core or another cache, or one cache is communicating data to another cache, let's say, and large amounts of data, streaming data. And this was a low latency, high bandwidth static network that was statically configured using circuit switching, meaning the path was set up and only that communication took place between two cores. Of course, if 2 other cores are communicating with each other and they don't have overlap, they could also communicate on this network. So clearly you can see that these networks are specialized for different communication patterns, let's say, and this is an example of a heterogeneous interconnect. And there are more examples of this actually, which we may talk about when we talk about interconnects. And there are many examples from life also. Heterogeneity is abundant in life, both in nature and human-made components. Humans are heterogeneous, clearly. We are all different, and we're all unique. I don't think there's any homogeneity example. Even twins are not really completely homogeneous with each other in terms of their behavior, for example. Cells are heterogeneous, specialized for different tasks, for example. Organs are heterogeneous, again, specialized for different tasks. Cars are heterogeneous, so you could keep adding to all of this, basically. Rooms are heterogeneous. There is no homogeneity that exists. Homogeneity is not the common case, I will say, in real life and human design. Okay, so let's talk about general purpose or special purpose. Asymmetry is really a way of enabling specialization, as I said. It really is a way to bridge gap between purely general purpose and purely special purpose. So purely general purpose means you don't have any specialized components. So you don't even have, for example, vector extensions. So if you think about it, vector extensions is a level of specialization added to a general purpose ISA, because clearly you could do all of those in a general purpose ISA, right? Why are you adding vector extensions? Well, because some applications make use of it a lot. And as a result, those applications can run much faster and much more energy efficiently. Another example is floating point instructions. So floating point computation, again, you could do all of that using integer computation. You just need to run more code, more instructions, right? You don't really need floating point operations in your instruction set architecture. In fact, the x86 architecture did not have floating point instructions for a long time. And then the x87 coprocessor was added to execute in a specialized manner the floating point instructions, etc. And then the rest is history. Now floating point instructions are an integral part of x86 clearly. So that's a special purpose acceleration mechanism clearly. But general purpose, fundamentally, general purpose doesn't need any of those special purpose mechanisms. But having heterogeneity bridges the gap between purely general purpose and purely special purpose. So I've been talking about general purpose. Special purpose, purely special purpose on the one hand is you don't have any general purpose capability, right? You're just designed to do vector instructions, as we have seen in digital design and computer architecture. Okay, so purely general purpose, single design for every workload or metric, as we've discussed. Purely special purpose, single design per workload or metric. Whereas asymmetric is multiple sub-designs optimized for sets of workloads and glued together. So you can think about this as you have some general purpose substrate, and then you add this part to actually execute this workload really well, x87 floating point processor, for example. And then you have this part to execute vector instructions really well, and you have this part to execute, I don't know, some other instruction really, some other workload, AI workloads, for example, really well for some reason. Maybe you have a small part in your machine that is capable of doing processing in non-volatile memory. So you could, the sky is the limit in the end with asymmetric designs. And that's why the design complexity is also high with asymmetric design compared to purely general purpose, of course. It's debatable if the design complexity is very high compared to purely special purpose, depending on what you have. So there's one question: does ARM have also SIMD instructions? How can you include these special instructions in a RISC architecture? So yeah, ARM also has SIMD instructions. Absolutely, yeah. I don't remember what they were called. Maybe someone can recall what they are. But these SIMD instructions are actually very important today because of media processing workloads. Again, in a RISC architecture, you can essentially, now you're actually going into maybe the religious aspect between RISC and CISC. It's not, so RISC means relatively simple instructions, right? It depends on what you consider SIMD instructions. It could be relatively simple instructions, but I understand your point. Basically, you're thinking that it's a complex instruction. And it is in some sense complex because you're operating on multiple data elements at the same time. And you also need to provide registers to operate on multiple data elements, et cetera, et cetera. There are many things. But basically, I guess the pure RISC concept, if you're really pure in your RISC concept, reduced instruction set computing concept, then I guess what happens is these should not be part of it. But I think ARM bridged that, ARM crossed that bridge a long time ago before including the vector instructions. So basically, in the end, none of the ISAs that are out there today are, in my opinion, pure RISC ISAs. They have every ISA has some components of RISC. Of course, x86 is clearly complex. I can say that because it has everything almost. But I think if you look at the other ISAs, they've quickly evolved to figure out that, okay, maybe going extremely simple is not the right thing to do. Maybe we should add these special purpose things that workloads benefit from. So if you think about the early RISC, for example, let me give you an example, I guess, from MIPS. MIPS is one of the pure early RISC architectures. And initially, it did not have multiplication, let's say. In the early versions of multiplication, it did not have multiplication. Okay. If you're really RISC, meaning if your philosophy is very hardcore, almost zealously RISC, then that's probably the right thing to do, right? Because why do you need multiplication? You can have add and shifts. Now, if you could take it even further, right? Do you really need add? Well, they didn't go that far because they thought add was important, and it's important, no question about that. But I mean, add you don't need also, right? Why do you need add? You could use and not, and you're functionally complete. And you add shifts to make your life easier, and then you're fully functionally, functionally complete plus easy life, let's say. So clearly, RISC concept is a continuum also, and you could stretch it to maximum levels. But they quickly figured out that it was a bad idea not to have multiplication, let's say. And they quickly added multiplication because there are enough programs that require a fast multiplication mechanism. You don't want to do it with adds and shifts in the end. And I think they didn't need to experience the hard way to decide that they needed an add instruction. I think so. I think basically this is a philosophy in the end, and I think there's no pure RISC architecture that exists outside today. And again, I think there was unfortunately a time in a computer architecture where there was a religious debate due to RISC versus CISC debate. In the end, I think a lot of architectures have components of both. For example, IBM Power is another great example. IBM Power architecture was initially designed to be I guess, called, let's say, maybe not designed to be, that's probably the wrong words, but called a risk architecture. But if you look at the instructions over there, some of them are extremely powerful instructions. I think you have decrement and branch if not zero, for example. I wouldn't call that a risk instruction, right? You're doing both decrement and branch if not zero. That's one example. You also have example of cache copy instructions, for example. That's not necessarily a risk instruction. But that's a very good point. I see that Jisung provided. Okay, Neon, yes. Thank you, Neon. thank you, Jisung. Yeah, that's the name of the ARM extensions, as you can see. You can read more about them. Okay, so the goal of a good asymmetric design is to get the best of both general purpose and special purpose in the end. You don't want to be completely special purpose. And you could potentially be that way also, right? An asymmetric design have extremely special purpose things, and you glue them together, and you can execute 1,000 workloads really well, except you have 1,000 different processors executing each workload. So that's asymmetric, obviously. So that's an example of asymmetry, but that's not what we're going to target here. We still want to remain general purpose as much as possible because there are benefits to it, but there are benefits to specialization as well. So we want to specialize too. Okay, let's talk about advantages and disadvantages before we go into more in this lecture. Basically, clearly asymmetric designs have advantages over symmetric design. You can enable optimization of multiple metrics, as we discussed. You can enable better adaptation to workload behavior. You can provide special purpose benefits with general purpose usability and flexibility. That sounds good. But unfortunately, you have higher overhead and more complexity in design and verification, clearly, because symmetric design, you can design one component and you can basically stamp it out, right? Whereas asymmetric design, you have to design and verify each component. You have higher overhead in management. Your scheduling decisions need to consider the asymmetry and workload match to the different resources. You have overhead in switching between multiple components. Potentially, if you decide to, okay, you're executing on a big core, you decide to switch to a small core. Well, there's an overhead. At the very least, you need to warm up your caches in the small core. And if you're going or flush the pipeline also, right, in the large core. And switch can happen between a CPU and a GPU also, potentially, right? So you actually have overheads in terms of asymmetry whenever you need to exploit it. So there's design overhead, verification overhead, but there's also system level exploitation overhead that are more dynamic. So yet another example I just mentioned, actually, modern processors integrate general purpose cores and GPUs. So CPU, GPU systems is another example. Here, the heterogeneity is not just in microarchitecture level, but also in execution models and ISAs, clearly in CPU, GPU. So they have complete different ISAs for CPUs and GPUs. You have completely different programming models and execution models as well. So whenever you're offloading code between CPU and GPU, you need to take that into account. And contrast this with heterogeneity in only microarchitecture. So these are, heterogeneity can happen at multiple levels as well, you can see. Okay, so we've been talking about some key problems in future systems, and I believe all of those have room to be solved in with using heterogeneity. And clearly, we've talked about memory system, right? I'm not going to talk more about that at this point. We've been talking about efficiency, performance, energy, and that affects your scalability. And clearly, this leads to a lot of benefits in future systems. And predictability and robustness, we've also been talking about a lot, right? And we've also already talked about everything on this slide as much as possible. But basically, asymmetric designs can help solve these problems. And we've seen examples of asymmetry in all of these, which I'm not going to reiterate right now. But the rest of this lecture is going to focus more on performance, parallelism, efficiency, and scalability overall. When I say efficiency, it's not just energy efficiency, although energy efficiency will also improve, but it's really more about scalability and parallelism of the system and how we can potentially take advantage of heterogeneity to enable that. And we're going to look a lot into the computation right now. So we've been talking a lot about memory, clearly. As I mentioned, this course will start with memory, and we've covered in almost 2/3 of the course memory, but later we're going to focus more on computation, and this is where we start on computation as much, computation. So before I go into that, let me give you some commercial asymmetric design examples. Clearly integrated CPU and GPU systems exist. They're used, CPU plus many hardware accelerators. Your cell phone is clearly one example. Heterogeneous multi-core systems also exist. I mentioned the IBM Cell at one point. ARM's big little system is a heterogeneous multi-core. CPU plus FPGA systems exist. So there's heterogeneity in the processing unit level, as you can see over here. And sometimes at the ISA level also, right? In fact, CPU plus FPGA is all about heterogeneity at the ISA level. What kind of ISA do you have for FPGA? The answer is none, because there's no ISA for an FPGA today, right? You basically go directly from algorithm to logic in the end. You could potentially construct a middle layer, but it's not an ISA in the end. So clearly these have different types of heterogeneity also. So it's good to think about that. And these are all commercial. So commercially, heterogeneity has already proven itself. And you can see that hybrid memory systems, I'm not going to talk about the memory system, since I said we're going to talk about computing systems right now. So we're going to focus on the computing part. And you can maybe find other examples over here. And this is asymmetry, or heterogeneity is increasing. You've seen this picture before. We have more heterogeneous agents. It's going to increase even more. We have heterogeneous memories, as we've talked a lot about, and we have heterogeneous interconnects, as we talked, and we're going to talk more about. Now let's focus on this multi-core system design, and I'll give you a heterogeneous perspective of it, because initially when multi-core systems were designed, they were not heterogeneous, but now they're increasingly heterogeneous, and we will see reasons for it. And you've seen this picture earlier. This is actually a relatively old picture that looks at the trend in industry, which is clearly putting multi-cores or many cores on a chip is simpler and lower power than putting a very large core, because we don't know how to scale that large core for various reasons, in terms of performance, in terms of complexity, in terms of verification capability, and in terms of energy efficiency of the algorithms that go into that single large core. As a result, it's a lot easier to design a single core and stamp it out. So that's what people have done initially. These are not the earliest multi-cores, actually, clearly. IBM Cell is the earliest heterogeneous multi-core. That's the only different one over here. Let me put it that way. Everything else is a homogeneous multi-core system. And you can see some of them are networked, meaning network on chip. And these are some of the smallest cores are actually here in the GPUs, as well as the tile engine. So I'm going to give you a historical perspective of how these cores have been designed. So with many cores have on a chip, what we want is really n times the performance with n times the cores when we parallelize an application on n cores. So I looked at this in some different way when we talked about interference. So we're not going to talk about multiple applications right now. We're going to talk about a single application. So a single application, I want to parallelize it on these 4 cores, let's say. And if I use 4 cores, I should get 4x the performance of a single threaded version of that application, right? That's linear scaling. We're going to talk more about that when we talk about multiprocessors, but let's assume that that's what we want. And that's a reasonable thing to ask clearly. You have 1 core, you get performance level X. You have 4 cores, you want performance level 4x. Now, if you don't get performance level 4x, then you're actually not utilizing your cores really well. Okay, but what we get is Dahls Law. Hopefully all of you know. This is due to serialization bottlenecks. And also there are bottlenecks in the parallel portion of the program. So let's cover these, because this is going to be fundamental to what we're going to discuss next. And this is going to be fundamental to all of the computation related issues. And clearly Dahls Law is applicable much beyond. So what Dahl did is actually formulate this law. Basically, he did a lot of empirical studies in 1960s, where he looked at data intensive workloads, and he basically looked at parallelizing those workloads. And he basically said, unless your parallelizable fraction is really high, you don't get a lot of benefit from multiprocessors, let's say, parallelizing. And I think the workloads that he had a parallelizable fraction of 60%. And today we know that if your parallelizable fraction is 60%, the maximum speed up you're going to get with infinite number of processors is 2.5, right? Because non-parallelizable fraction of is 40%. And as a result, your speed up is 1 divided by 0.4. Okay, so he formulated that. And that's why he titled this paper saying validity of the single processor approach to achieving large scale computing capabilities. Basically, he said that single processor approach is much less effort than parallelizing your program, especially if your parallelizable fraction is low. So that's Dahls Law, basically. So you have the parallelizable fraction of a program, and you have the number of processors. Your speed up with n processors compared to 1 processor is an equation like this. 1 divided by the the serial fraction, which you cannot parallelize. It has to be executed in only one processor, plus the parallel fraction divided by the number of processors you have. So as n goes to infinity, as number of processors goes to infinity, this term becomes 0 or gets close to 0. And you're left with speed up 1 divided by 1 minus f, whereas f is the parallelizable fraction of the program. So basically, 1 minus f is the serial fraction of the program. Call that, let's say, alpha. Basically, your speed up is 1 divided by alpha, assuming n goes to infinity. There's another assumption over here, which we will talk about. But basically, if f is 50%, you get 2x speed up with infinite number of cores. Sounds terrible. If f is 90%, you get 10x speed up of 10. If f is 99%, you get a speed up of 100. Now it's getting better. If f is 99.9%, you get a speed up of 1,000. Now you see what I'm getting at, right? So your f needs to be really large for you to get very high speed ups. And this is an exponential curve, actually, if you plot it, as we will see later on. Okay, so this clearly imposes a bottleneck on parallelism, which is the serial bottleneck. This is called the serial bottleneck. Your bottleneck by serialization or serialized fraction of your code, or non-parallelizable fraction of your code. Okay. This Dahls law is actually not perfect. It's a good way of really thinking about serial versus parallel, right? But it doesn't. What it doesn't really tell you, it tells you a distinction between serial and parallel, and it assumes that your parallel is perfectly parallelizable, right? But that's not the case in real life. So basically, this assumption that f divided n doesn't hold in real life in many cases. This is a good first order approximation, no question about that. But you may actually run into bottlenecks in this parallel portion also. And that's what I call caveats of parallelism. That's why this is a very fundamental and important slide, basically. One caveat is your serial fraction. The other caveat is what's going on here. Are you actually dividing f divided with n whenever you have n processors? And the answer is no. And there are three fundamental reasons why, even though you may have n processors and you've divided your program into n processors, you cannot get f divided by n like this. And three reasons, well, we've already talked about 1 minus f. Maximum speed up is limited by your serial portion. That's called the serial bottleneck. But your parallel portion is usually not perfectly parallel as well. So your maximum speed up is also limited by this part. And let's take a look at that. And there are three reasons, as I said, why your parallel portion is not perfectly parallel, and this f divided by n doesn't always hold. Synchronization. Whenever you're updating shared data, for example, all of the other threads may be stalling, right? Why? Because they're waiting for the shared data update to happen. This is the critical sections that we talked about earlier, which we're going to talk about even more. This synchronization overhead basically ensures that while you're synchronizing, this f divided by n doesn't hold, right? Okay, so this is one fundamental reason why parallel portion is not perfectly parallel. Another fundamental reason we talked about also, load imbalance, right? Remember barrier and threads reaching a barrier in box synchronous programming. Because of imperfect parallelization, threads make different amounts of progress, and we discussed the reasons for imperfect parallelization. Programmer may have distributed the tasks unevenly to the threads, or even if the programmer distributes the tasks evenly, internally the tasks have different input sets, different types of input that can be executed at different amounts of time. As a result, different processors make different progress, and in the end, you're very much bottlenecked by the last thread that's finishing its load. Okay, so if you have load imbalance, this doesn't hold also. You cannot divide f divided by n easily. And in extreme cases, load imbalance can be really bad, and you may actually get very close to f divided by 1, depending on how your load imbalance is, clearly, right? Okay, so that's the second reason. And the last reason is resource sharing overhead. Basically, this is also very fundamental, and we've seen this as well. This is really contention among n processors for physical resources. So you can divide f by n, assuming that the threads are not interfering with each other, right? Assuming that you've divide by your threads into different cores, and these cores are never interfering with each other. And assuming you don't have load imbalance, and assuming you don't have synchronization. Even if you don't have these two for some reason, this resource sharing is, as we discussed, is a very tough assumption also. Basically, whenever two threads need to access the same bank, one of them gets delayed. As a result, you cannot easily divide this f by n also. So these three fundamental reasons bottleneck the parallel portion, and clearly serial bottlenecks how much speed up you can get overall. So unfortunately, there's no model that easily takes into account this parallel portion, because it's just not easy. It's not, you could potentially come up with an analytical model that takes into account parameters that express synchronization, load imbalance, and resource sharing. But it's not easy, actually. As far as I know, there's no model that takes that into account. So keep that in mind. Whenever you see Dahls Law, you should always think about this as well. So even Dahl was potentially optimistic because he assumed perfect parallelizability, right? But that's not true in real life in many programs, especially in irregular programs. In some regular programs, yes, you may get very close to f divided by n, but in many programs, you don't get as close to f divided by n. And the difficulty in parallel programming is actually, we will discuss this when we get to multiprocessors again, but since we're talking about parallelism, the difficulty in parallel programming is really about maximizing f as much as possible, thereby minimizing 1 minus f, clearly. But also, it's about minimizing f divided by n. So you cannot just maximize f, but you also want to minimize f divided by n if you want to maximize your parallels. And clearly, there's a lot that needs to go on to minimize f divided by n. You need to solve the synchronization issues, you need to solve the load imbalance issues, and you need to solve the resource contention or resource sharing overhead somehow. And clearly, these require different solutions, right? They're not the same problem. That's why these are orthogonal over here. Your resource contention is completely independent of what you do in your program. Well, not completely independent. There's some dependence over there, but in a sense, programmer may have eliminated your synchronization and load imbalance, but you may have resource contention, right, between different threads of your same program. Okay. So this is a very fundamental slide, and I've been using the slide for a long time now, and I think this is a very good summary of parallelism in a nutshell, let's say, at least multiprocessor parallelism in a nutshell. And it's important to keep everything in mind in the slides. And if you come up with a third reason over here, I would love to know. So far, all of the attempts from anyone to come up with a third reason that is not covered in some way by these three reasons have failed. Usually, the third reason people come up with is actually a special case or a different way of saying one of these three reasons. For example, communication. You can say communication between cores. Okay, yes, communication is really about synchronization and load imbalance, right? In the end. So communication is actually very imprecise, let's say, as to why parallel portion is not parallel. Okay, so let me go into some more detail over here. So basically, many parallel programs cannot be parallelized completely. And this is a big issue with parallelization. You run into serialized code sections. And there are many causes of serialized code sections. I'll give you 4 of these over here. And we've covered all of these, except for maybe the first one. But first one's obvious. You have sequential portions that are not parallelized. There's only one thread that's executing them. This is what Dahl was concerned about. It was his serial part. And then we talked about critical sections where only one thread can be present. We talked about barriers where threads are reaching a barrier point so that they could synchronize and go on. And we talk about limiter stage and pipeline programs also, if you remember when we talked about parallel memory scheduling, right? And serialized code sections, unfortunately, are not good for performance because they serialize the program. They limit scalability, and they also waste energy. So they're actually bad for performance, scalability, and energy. So we're going to talk about scalability more, especially in the next lecture. But scalability means how well your performance increases with the number of cores you add to the system. And at some point, your performance stops increasing and starts reducing, actually, as we will also see, because you have some additional overheads of this that we discussed. Okay, let me give you one example of this actually very quickly. MySQL is a popular open source database, and this, at the very high level, MySQL operates by opening some database tables and performing some operations specified by the queries that are sent to MySQL. Okay, so this part is parallel. Opening the database tables requires accessing the open tables cache. So this is the critical section, meaning only one thread can be executing this. Of course, you can do fine-grained synchronization, etc. Let's assume that it's all done and there's some critical section over here. And this is a classic speed up or scalability curve that you see in a parallelized program. So on the x-axis, you see chip area. On the y-axis, speed up normalized to a single thread or single core. We're going to assume, without loss of generalization, that a single core can execute single thread, okay, to make life easy. Clearly, this is the normalization point. At 16 cores, you peak at 6x speed up, which is not terrible, actually, but it's clearly not linear speed up, linear scalability. Linear should have been 16. At 16 cores, you should reach 16, right? Okay. But after that, performance starts reducing. Why? Because now you're adding more threads and you have more cores. And these cores have more synchronization overhead because they need to synchronize to some memory variables, locks, let's say, and that lock needs to go from one core's cache to another core's cache, right? So you need to communicate this lock more often, as well as across more hops. And that increases the latencies of synchronization. And as a result, the performance starts going down due to that contention. You're not getting enough benefit from more threads, but you're just getting overhead, more overhead, essentially. Okay, so that's the downside of parallelization. At some point, you also need to know how much to parallelize, right? Because at some point, your synchronization, load imbalance, resource contention, there could be resource contention effects also here, by the way. I'm not talking about those, but your memory bandwidth may not satisfy all of these threads, for example. But basically, because of all of those bottlenecks in the parallel portion, your performance starts going down compared to the peak point. So the peak point is called the maximum scalability point. Basically, this workload is scalable on this system up to 16 threads or 16 cores, let's say. After that point, the performance degrades. Okay, so you need to be very careful at what number of threads you operate your workload, clearly, right? If you want to take advantage of your system in the best possible way. So I'm going to show you a mechanism, and asymmetric design actually can take your system to a much better place. And this is old results, clearly, so you can actually do much better than that today. So we're going to talk about that later on. But let me talk about the demands in different code sections. So now we're going to start to specialize for different code sections, as much as not too much specialization, but some level of specialization. So clearly, these different code sections need different things. In a serialized code section, we really want a one powerful large core that can execute very fast and get rid of get out of this code section very quickly, assuming you're bottlenecked by computation. In a parallel code section, we want many wimpy small cores because you're perfect. Let's assume that you parallelize your code really well, right? And these clearly conflict with each other, right? If you have a single powerful core, you cannot have many cores because you don't have, assuming you have limited area budget, limited cost. A small core is much more energy and area efficient than a large core, clearly. So let's take a look at these large versus small cores. Think about digital design and computer architecture a little bit. Large core, we've seen a lot of techniques actually to construct this large core. Out of order execution, wide fetch superscalar, deeper pipelines, aggressive branch prediction. We've actually seen different branch predictors, multiple function units, caching mechanisms, trace caching, and memory dependent speculation mechanisms, which we also talked about. Small core doesn't have a lot of complexity, in order, narrow fetch, shallow pipeline, simple branch predictor, if at all, few functional units. So clearly, these are two different approaches of building a multi-core system. And industry actually looked at both approaches. And we're going to assume this, and this is actually not a bad ballpark. Large cores are power inefficient. So for example, to get 2x the performance, you need 4x the area. In the general purpose case, actually some folks have done studies that show that this is the case. It doesn't hold generally, of course. If you look at a specific workload, it doesn't hold. But if you average across many workloads, something like this may hold. Okay, so this is an example from one of the papers that I mentioned earlier from Intel. And these Intel folks actually looked at getting the best of both latency and throughput by using dynamic heterogeneity. And they looked at large core and small cores, and they basically say the same thing here. Large core is very hefty. You can see the large core has a large width, out of order, pipeline depth is much longer than small core. but normalized performance is much higher. You can see normalized power is also much higher, unfortunately, and normalized to small core, as you can see over here. But normalized energy per instruction is also much higher. So given the same instruction, the energy per instruction here is much higher, but your performance is also much higher. So keep that in mind. So at a given point in time, you may decide to execute many small cores or one large core. Okay, let's talk about some of these large and small cores. When industry was first designing multi-core architectures, IBM Power 4 was one of the earliest designs. And this is a beautiful paper that describes IBM Power 4. And it was symmetric. So some folks in the industry decided to design large symmetric cores. Some folks in the industry decided to design wimpy small cores. So a Power 4 is a symmetric multi-core chip, and it has two powerful cores. I'm not going to go into details, but these are examples. At the time, this was actually one of the most powerful chips, and this is 2004 we're talking about. Actually, IBM designed much earlier. You can see large instruction windows, reasonably large instruction windows for its time, 8-wide instruction fetch as you execute, large branch predictor, large cache, reasonably large cache, and aggressive prefetching mechanisms. And IBM Power 5 on top of this added multi-threading. You can see simultaneous multi-threading. And you can read about this also. So it added a little bit more parallelism to it, but the core was similarly large. This is one example. The other direction is small, basically designing small cores. And Sun took the exact opposite approach compared to IBM. IBM said basically we cannot lose performance. We have to actually have large cores because we're executing these workloads that are legacy, and they cannot be rewritten basically. So we cannot go from a large core that we have right now to a small core. So we have to replicate large cores. Whereas Sun said, okay, we're going to trust that folks who are writing web server applications, transaction processing applications are going to rewrite their applications. Well, Sun doesn't exist anymore. So that tells you something perhaps. But this is actually also telling because they relied on software changing significantly. And some people actually changed, some people didn't change. But basically what they did was they designed a processor that is not out of order. Their previous design, they designed a processor that's very, very simple actually, as we will see in the next slide. And this is actually a very beautiful paper that talks about simple in-order multi-cores systems. So compared to their previous design, actually, this was actually much worse in terms of single thread performance. But basically, this is a Niagara core. It's 4-way fine-grained multithreading. If you remember fine-grained multithreading, you don't need branch prediction over here. So you basically feed in one instruction every n cycles, and you don't need data dependency checking. Basically, you feed in one instruction every n cycles, and you ensure that you ensure that you have enough threads to cover n. In this case, they decide 4 branches resolve after 4 cycles here, as you can see. It's dual issue in order, and you have shared floating point unit among cores. You don't even have different floating point units in different cores. And you can see the different things that go into fine-grained multithreading. We actually covered this a little bit when we talked about fine-grained multithreading, digital design, and computer architecture. So if you want to refresh your memory, you can take a look at that lecture. But remember the demands. In a serialized section, neither of these multi-core systems is good enough in a sense, because in a serialized code section, we wanted one powerful large core. In a parallel code section, we want many wimpy small cores, and they conflict with each other as we discussed. The question is, can we get the best of both worlds? So let's take a look. Let's do some analysis. Assumptions is we have a small core that takes an area budget of 1 and has performance of 1. We have a large core that takes an area budget of 4 and has performance of 2, based on the square root law that we discussed, which is you have your normalized performance is the square root of your normalized area compared to a small core. Okay, so tile large approach is taken by multiple companies, as you can see, IBM, AMD, Intel, and you get you look something like this, assuming you have 16 small core area budget, you divide into 4 large cores. You get high performance on single thread serial code sections, basically 2 units of performance as opposed to 1 unit. And you get low throughput on parallel program portions, unfortunately, because you have 2 units in each of the large cores and you have 4 of them, right? Okay, that's 8 units. Now, tile small approach is done by some other folks. Even Intel actually had some experiments with this, Larrabee, which was supposed to replace GPUs, but it didn't because of difficulties in software adaptation to Larrabee. and tile area actually is the ultra small part. The big advantage of tile small is you get high throughput on the parallel part, 16 units, because you have 16 small cores here. You get low performance on the serial part, single thread, you have 1 unit. So your performance actually halves compared to the 2 units in the large approach. So, but the key question is, can we get the best of both worlds? So clearly, this is a positive, this is a positive. Ideally, we would like to get the positives as much as possible while avoiding negatives as much as possible, right? Especially, we want to avoid this. We don't want reduced single thread performance compared to existing single thread processors. So that was a big mistake of going from large core to small core, basically. And the idea is very simple here. Have both large and small cores on the same chip. Have performance asymmetry while keeping the architecture the same. Have microarchitectural asymmetry. And that's the idea of asymmetric multicore. This is also called asymmetric chip multiprocessor, ACMP. You provide one large core and many small cores. If your area budget is 16 small cores, this is an example of what you would provide. And the positive is when you're running serial code portions, you get 2 units of performance. And when you're running parallel code portions, you don't do too badly compared to this. You get 12 plus 2 units. And if you actually do multi-threading in the large core, you get even more. In that case, basically, you can match the performance of tile small almost by doing multi-threading over here. That's the idea, basically. And how do you accelerate a serial bottleneck? When you have single thread that gets executed on the large core. When you spawn more threads, they get spawned in the parallel portion, they get spawned on the small cores. And they keep executing. When you go back to the single thread, you execute on the large core again. Okay, this is an example of the serial bottleneck. Clearly, the single thread is a serial bottleneck over here. So let's take a look at what I've shown you earlier. I'm not going to go through the details again, but clearly this tile large approach, tile small approach, and ACMP, we're comparing them. Large cores are actually the number of cores you can see over here, the number of large cores, small cores. In terms of serial performance, okay, let me do it that way. In terms of serial performance, this asymmetric multicore processor actually matches the best. In terms of parallel performance, asymmetric multicore processor almost matches the best, which is the symmetric SCMP or tile small approach. But again, as I said, if you have multi-threading over here, you could match 16 also over here. But you cannot match, without having a large core, you cannot match this 2 over here. So that's the idea. So that changes Dahls Law a little bit, actually. So I'm going to spend a little bit more time to finish to a good point, and we're going to make up for it later on. But basically, an asymmetric multiprocessor has a different type of Dahls Law, because now it looks like this, basically. Because your serial portions execute on the large core, your parallel portions execute on both small cores and the large cores. Now your parallelizable fraction of a program is divided by a number of large processors, basically a number of small processors. This is the n we had in the previous version. But clearly it's not n here, because right now n is equal to L plus S. The total number of processors you have is L plus S. But with assuming there are no issues with the 3 issues with the parallel portion, as we discussed, let's assume that the number of speed up of a large processor over a small one is X. You can speed up the parallel fraction by S number of processors plus L number of processors times X, because X gives you the power of that many small processors for a given large processor. Okay, so hopefully this is kind of obvious. If you think about it, you will see that it's obvious. We're trying to divide by the processing power overall over here, assuming that you don't have bottlenecks in the parallel portion. And the serial fraction is also divided by something here, which is good, which is X over here, right? That sounds good now, right? Because previously your 1 minus F was not divided by anything. If your 1 minus F is divided by, I don't know, if this X is 4, that's great. You're speeding up your serial portion also when you go to a multi-core. Okay, here actually it's you can make it very close to L plus. What should I say over here? You can make it very close to N essentially in the end. Okay, so let's revisit the caveats of parallelism. So this is the older equation, if you will. So basically, we're going to talk about accelerating parallel bottlenecks also. Essentially, serialized or imbalanced execution in the parallel portion can also benefit from a large core. So far we've been talking about accelerating serial bottlenecks, right? We're accelerating the serial bottleneck. We have not changed much over here. If you do things right, this is really equal to n in the end, or it should be equal to n, where n is the number of small processor equivalents that you have. But clearly we have parallel bottlenecks as well, and that could also benefit from a large core. For example, whenever you have critical sections that are contended, you could ship that critical section to a large core. Whenever parallel stages take longer than others to execute, you could ship that to a large core as well. And the key idea we're going to examine in the next lecture is to dynamically identify these code portions that cause serialization and execute them on a large core. And this is where I'm going to stop. This is a good place to stop. We're going to start with the idea tomorrow of accelerated critical sections. And this is going to be one example of accelerating bottlenecks. And we're going to generalize it. And we're going to look at a bunch of issues in accelerating these critical sections, which is really the parallel bottlenecks in the parallel portion. Because hopefully you're convinced that serial bottlenecks should really be executed in a large core because it's serial, it's single thread. But parallel bottlenecks, we will see that they also can be executed. Okay, let me see. There's one question. It seems generally simpler in terms of efforts to change software rather than hardware. Then why do we see the successful trend of hardware optimizing for the legacy software codes instead of putting in aggressive efforts so that software adapts to better hardware architecture? Well, I mean, sometimes it's simple to change hardware, but actually software is not as easy to change. I would not agree with that completely. It depends on what you change in software, clearly. Clearly, software changes can be done without hardware cycles. So I think that's what you mean, probably. Without, you can actually change software much more easily without requiring new hardware. That's true. But let me see. Then why do we see the successful trend of hardware optimizing for legacy software codes instead of putting in aggressive efforts? Well, I think both of them are being done basically today. Hardware can optimize for not just legacy. So what I'm going to describe is not going to be just legacy, but you could actually execute legacy also. But you could also design your software to adapt to a heterogeneous system, as we will discuss. But people are also whenever a new hardware comes up, people are also changing their hardware, changing their software to adapt to better hardware. So I think things are, as I said, movement is not just in one direction today. You do want support for legacy for sure, and that helps. And that helps some software to actually run faster in existing hardware. And that's one of the reasons why people do it, is because hardware changes have enabled very high performance improvements for decades and decades without software having to do anything. And that was actually one of the big discussion points. People basically said, do I want to optimize my software, or do I just wait for the next generation hardware? And this was real, actually. In high performance computing, for example, people decided not to specialize their software or re-optimize their software in some cases, because they said 1 year later, Intel will come up with a better hardware and I'll get 20% more, or I don't know how much more. I'll get 60% more. At that time, it was more 60%. I'll get 60% more. If I put all the effort to optimize my software, I'm not going to get 60% more. So I'm going to sit still and add something else, do something else, basically. And that was actually the real mindset whenever the hardware was improving really fast. And I think there are enough folks in the world, and there's enough software in the world that faster hardware transparently can enable legacy software. But that said, what we're going to discuss is really hardware software co-design in the end. So you may need to change your software also to take advantage of what we're going to discuss next. Okay. Any other questions? Okay, I guess not. So this is a good place to stop. We will continue to discuss these fascinating topics starting from accelerated critical sections tomorrow. Take care and see you tomorrow.